The distant starlight problem is the most difficult problem faced by creation scientists. The problem is, how can we see distant starlight in a universe that is billions of light years across but only 6,000 years old? The simplest and most obvious solution would be to throw out the biblical date, as some Christians have. However, simply going with the simplest and obvious solution is just a form of giving up. It is a lazy way of simply avoiding the effort it might take to solve the problem. The fact that this type of compromise makes those Christians look good to the world has an added attraction to it. Over the years, many solutions have been offered, and they include light being created in transit, the speed of light slowing over time, and various forms of time dilation. Dr. Jason Lisle has proposed that the Bible uses what is called the Anisotropic Synchrony Convention that results from special relativity. In this video, we will look at the details of the Anisotropic Synchrony Convention and how it solves the distant starlight problem. When does an event occur in spacetime? Surprisingly, this is not an easy question to answer because, based on relativity, there is no specific answer. Different observers will see different events as simultaneous. Furthermore, it turns out that there are conventions that you can choose that will change the events you see as simultaneous in distant points of space. If you have a spacecraft passed by the Earth with a relative speed of nearly the speed of light, from the perspective of someone on board the ship, two flashes occur at the same time. Someone on Earth will see these events differently. First, they will see the event at the rear of the spacecraft occur. Then they will see the event at the front of the spacecraft occur. Those on the spacecraft literally have a different idea of now than those on the Earth do, as their coordinate systems are tilted with respect to each other. Now let's take the case of a ship traveling really close to the speed of light relative to the Earth. One day, they both observe a star, called a supernova, in the Large Magellanic Cloud. According to the person on Earth, the supernova happened 148,000 years ago. But according to the person on board the ship, it happened only 21 years ago. Here are various events occurring in spacetime at various distances from Earth as seen from Earth. Here is a comparison with those same events in spacetime as seen from a ship traveling at half the speed of light relative to the Earth. Here is a comparison with a chart of the same events in spacetime from a spacecraft going at 0.9 times the speed of light. What this means is that there is no absolute notion of what is happening now. Not only is an observer's perspective on what is happening right now dependent upon relative velocity, it also depends on the clock synchronicity convention that is being used. At the heart of this is the speed of light and the impossibility of measuring the one-way speed of light. The simplest way of measuring the speed of light is sending a pulse of light to a mirror and bouncing it back so that you have the time that it was sent and received based on the same clock. To measure the one-way speed of light, you need to send a pulse of light from one clock to another, with the two clocks being synchronized. The problem is that if these clocks are not synchronized perfectly, you will get erroneous figures. This is just a simple illustration of the problems that can arise when trying to measure the one-way speed of light. You might be saying at this point that you can measure the one-way speed of light as long as you and the clock are in the same frame of reference and the clocks are synchronized. However, the key problem here is that the clocks must be synchronized at a distance. When dealing with clock synchronicity, the first question is, what do we mean by clocks being synchronized? Naturally, the idea is that clocks are synchronized when they are showing the same time. However, the question is, from whose perspective are two clocks showing the same time? Now let's take the case of three observers at rest with respect to each other, but separated in space, each with a clock near them. If the guy in the middle sees the three clocks as synchronized, then the guy on the left sees them out of sync with the other two behind his and the one on the right further behind his than the one in the center. The woman on the right sees the clocks as out of sync, seeing the other two clocks as behind hers with the one on the left being further behind hers than the one in the center. If the guy on the left sees all three clocks as synchronized, then the guy in the center will see both of the other clocks behind his with the one on the right behind the one on the left. The woman on the right will see all three clocks as out of sync with the other two clocks behind hers, and she will see the one on the left as being further behind hers than the one in the center. If the woman on the right sees all three clocks as synchronized, then the guy in the center will see the other two clocks as behind his with the one on the left being a little ahead of the one on the right, and the guy on the left sees both of the other two clocks behind his with the one on the right further behind the one in the center. Despite the fact that these three observers are at rest with respect to each other, they do not agree on whether or not the clocks are synchronized. Neither do they agree as to the order in which they are out of sync. The question is who is right about whether or not the clocks are synchronized. Quite simply, a clock synchrony convention is a convention for synchronizing clocks across the universe. The selection of a clock synchrony convention is totally arbitrary. No one convention is right or wrong, they are simply conventions. Each convention makes an assumption about the one-way speed of light within certain constraints. To fully explain clock synchrony conventions, it is necessary to introduce the term proper velocity, v0. The proper velocity between any two objects would be the two-way or tangential velocity. Clock synchrony conventions concern themselves with radial velocity. Adjusting between clock synchrony conventions is pretty easy with the addition of this term to the main formulas, where epsilon is the adjustment factor between clock synchrony conventions. Epsilon equals 1/2 for the standard isotropic synchrony convention, 1 for the aisotropic synchrony convention, and 0 for the anti-isotropic synchrony convention. The entire range of epsilon, from 0 to 1, falls within the range of acceptable nows within relativity. What all this boils down to is how you synchronize clocks, that is, how do you determine what is now, is simply a convention under relativity. The math works for the entire range of possible conventions, so there is no one convention that can be said to be the truth. The observer is free to choose whichever convention he wants, and it can be for any reason, including that it is the simplest for his particular situation. However, among these arbitrary conventions, there are only two that have any practical or logical use. One is the Isotropic Synchrony Convention, in which the math is the simplest. The other is the Anisotropic Synchrony Convention, which most naturally matches what we actually observe. The Isotropic Synchrony Convention, also called the Einstein Synchrony Convention, is the standard convention used for the clock synchronicity in physics, astronomy, and cosmology. The problem is that most people do not realize that it is only one arbitrary convention among many, as well as one of two of these conventions that has practical applications. The primary convention for the Isotropic Synchrony Convention is that the one-way speed of light is the same for the observer in all directions, specifically that the incoming speed of light is the same as the outgoing speed of light, which is equivalent to the proper speed of light. It needs to be remembered that despite the fact that this convention is commonly used, it is still just a convention, and that under relativity, the one-way speed of light cannot be measured independent of a clock synchrony convention. Furthermore, within a given clock synchrony convention, the one-way speed of light will always be measured as what is assumed by the convention, while the two-way speed of light will always be the proper speed of light, that is, c. In the Isotropic Synchrony Convention, clocks are synchronized across space and not time, such that any time you look at a distant object, you are looking into the past. This also means that what is considered to be happening now, in distant parts of the universe, are totally inaccessible. Despite the fact that the Isotropic Synchrony Convention is the one that is generally used in physics, astronomy, and cosmology, it needs to be remembered that it is just a convention. According to relativity, there is no absolute now in the universe. This not only means that different reference frames have different nows, but what you consider now, even within a given reference frame, still depends upon how you synchronize clocks. The Isotropic Synchrony Convention may be the most commonly used synchrony convention, but it is still just a convention. That fact needs to be kept in mind as you look at the Anisotropic Synchrony Convention. The Anisotropic Synchrony Convention is one of two clock synchrony conventions that has practical applications. The primary convention of the Anisotropic Synchrony Convention is that the one-way speed of light is infinite when light is coming towards the observer and 1/2 c when heading away from the observer. It needs to be remembered that despite the fact that both conventions are just conventions and that under relativity, the one-way speed of light cannot be measured independent of a clock synchrony convention. Furthermore, within a given clock synchrony convention, the one-way speed of light will always be measured as what is assumed by that convention, while the two-way speed of light will always be the proper speed of light, that is, c. In the Anisotropic Synchrony Convention, clocks are synchronized across both space and time such that now in the Anisotropic Synchrony Convention is the past in the Isotropic Synchrony Convention. Another way of putting it is that in the Anisotropic Synchrony Convention, clocks are synchronized along the past light cone. The result is that in the anisotropic coordinate system, the past light cone is equivalent to the space axis. Here is the illustration showing the full range of epsilon equals 1 to epsilon equals 0. with the isosynchrony convention having an epsilon of 1/2, in the anisotropic synchrony convention has an epsilon equal to 1. Here are two spacetime diagrams illustrating this difference. Both of these are from observers that rested with each other and in the same location. The first one uses the isotropic synchrony convention and the second one the anisotropic synchrony convention. Note that the further ones are shifted up the time axis of the graph in the anisynchrony convention. So, we need to remember that according to relativity, there is no absolute now in the universe. This not only means that different reference frames have different nows, but what you consider now, even within a given frame of reference, still depends upon how you synchronize clocks. The anisotropic synchrony convention is a very practical convention in that events occur exactly when we see them occur and not at some time in the distant past. It is a very practical clock synchrony convention that has actually been used since ancient times. It is still used today in that astronomical events are timestamped as to when they are observed and not at some time in the past. Here is a generalization of the Lorentz transformation formulas as well as the other formulas for dealing with the various clock synchrony conventions. There is actually a pretty straightforward generalization of the formulas for the anisotropic synchrony convention. With these generalized formulas, you can check out all possible clock synchrony conventions for yourself. The key to these clock synchrony conventions is the adjustment factor, epsilon, which can have a value from 0 to 1. It covers the entire range from the surface of the past light cone to the surface of the future light cone. This yellow arrow not only represents the range that can be considered now, but also based on the shift resulting from different frames of reference. That means that there is nothing here outside the realm of standard relativity. Numerous ways have been proposed to synchronize clocks for measuring the one-way speed of light. However, they all have the same problem. They all assume a particular clock synchrony convention, even if the person proposing it does not realize it. The result is that when it is looked at in another clock synchrony convention, it produces the results expected from that convention. The most common proposal is to start with two clocks right next to each other so that they can be synchronized, and then move one of them out to a distance where it can be used to measure the one-way speed of light. The problem with this idea is that it involves moving one of the clocks, and according to special relativity, this very act would cause time dilation, throwing the clocks out of sync. The solution proposed is to move the clock so slowly that there will not be any significant time dilation. The problem is that an observer at each clock would see the other clock as out of sync with their clock. This would not be an effect of the speed of motion, but an effect of the distance traveled. Every clock synchronicity convention, other than the isotropic clock synchrony convention, takes this effect into account to some degree. In the anisotropic synchrony convention, if one of the observers did see the clocks as synchronized, then he would measure the incoming speed of light as being infinite and the outgoing speed of light as 1/2 c. Another common suggestion is to send the signal to both clocks from a central source that would set the clocks at the same time when they received the signal. The problem is that it assumes that the one-way speed of light is the same in both directions. Also, this would not even work for an observer of two clocks in a different frame of reference. He would still see them as out of sync. You still have the same problem as you did before, that observers by each clock would see the other clock as out of sync. Furthermore, if one of the observers did see both clocks as synchronized, they would measure an incoming pulse as traveling at infinite speed with an outgoing pulse traveling at 1/2 c. This is exactly what would be expected from the anisotropic synchrony convention. It has also been suggested to use a rod as a way of synchronizing two clocks at a distance. However, this fails to take into consideration the fact that no rod is perfectly rigid. Even a diamond rod would be sufficiently flexible to mess up a synchronization for measuring the one-way speed of light. Furthermore, we have the same problem that an observer at one clock would see the other clock as out of sync with theirs. And if one observer did see the other clock as synchronized with theirs, they would measure the incoming speed of light as infinite and the outgoing speed of light as 1/2 c. The point is that no matter how you try to synchronize clocks, you have to assume one of the clock synchrony conventions to do it. The result is that you always get measurements that are consistent with that clock synchrony convention. All attempts to measure the one-way speed of light suffer from one of three major flaws. The first is that they use a tangential direction, which will always produce the proper speed of light. The second is that they assume, without realizing it, the isotropic synchrony convention. Finally, they are actually measuring the two-way speed of light. This one is quite clever in that it measures the delay time between two mirrors, with the signals being detected by the same device and the delay being measured by one clock. However, the path of the light between the two mirrors is tangential to the detector. As a result, all clock synchrony conventions will measure the proper speed of light. What is at issue is the radial speed of light. This is an experiment that has been claimed as showing that there is no difference in the speed of light in different directions. First of all, this experiment was not designed to test clock synchrony conventions. It was designed to experimentally test whether or not the Earth's motion affects the speed of light. Second, the comparison of the pulse arrival times at detectors 1 and 2 is not made by the detectors themselves, but by the computer, which the light pulses between the two wheels is moving tangential to. As a result, all clock synchrony conventions would measure the speed of these pulses as being the proper speed of light, which is what this experiment did. At this point, you may be asking, wasn't the one-way speed of light measured with the moons of Jupiter by the Dutch astronomer Alaus Roemer in 1676? Well, not really. That was the interpretation he made of his observations of the intervals between eclipse times. This not only predated relativity, but it assumed an isotropic clock synchrony convention. Now, he succeeded in measuring the proper speed of light, because even in the anisotropic synchrony convention, the time dilation effect due to distance is related to the proper speed of light. However, it does not qualify as a measurement of the one-way speed of light in the absence of a clock synchrony convention. The point ultimately is that you cannot measure the one-way speed of light without assuming a particular clock synchrony convention. Once you have done that, you always get results consistent with that clock synchrony convention. The main argument used against non-isotropic synchrony conventions comes from the isotropic synchrony convention being so ingrained that they cannot think outside the box. The thinking is that it cannot be real, because after all, the isotropic synchrony convention is what is used. However, non-isotropic synchrony conventions come as naturally out of relativity, as is time dilation and length contraction. Another argument against non-isotropic synchrony conventions is why should light behave in a non-isotropic manner? While this is a legitimate question, it is ultimately a result of the way spacetime works. Ultimately, the answer is that because of the way spacetime works, you can arbitrarily choose a convention for synchronizing clocks as long as it falls within certain parameters, and light behaves accordingly. The most natural objection to a non-isotropic synchrony convention is that it doesn't work that way. Light takes a definite amount of time to travel from one point to another. This misses the fact that, from the perspective of a photon, the trip is actually instantaneous because moving at the speed of light, photons do not experience time. Ultimately, as with all motion, the motion of light is motion through spacetime, and how we see that motion varies depending upon how we look at it. The key to understanding the fallacy of all objections to non-isotropic synchrony conventions is that they are insisting that only one is valid. Based on the assumption that only one can be valid, they will insist that adopting a non-isotropic synchrony convention, under any circumstances, is going against modern astronomy. Once you realize that all clock synchrony conventions are equally valid, arbitrary conventions, the problem goes away. This one comes from Rational Wiki, an atheistic propaganda site that gets most of creation science wrong. I know this from first-hand experience of their treatment of a paper that I wrote and was published in Answers in Genesis's Answers journal. Surprisingly, in this case, they actually got the basics correct and recognized ASC has a perfectly acceptable, albeit obscure, subbranch of special relativity. This argument starts with a hypothetical mirror 5,000 light-years away and pointing so that it reflects light directly back at Earth. The argument is made that from a young Earth perspective, this mirror would not show anything to Earth for another 4,000 years, and that is true. However, it is not a problem because unless you can get a mirror out there at a speed greater than the speed of light, this argument is just a thought experiment. Furthermore, it actually shows that there is a way that this approach could be tested, at least in principle. Once again, this one comes from Rational Wiki. The claim is that this is just a change in coordinate systems and that it does not change reality. They then go on to indicate that being able to use a coordinate system where the Earth is fixed and stationary at the center of the universe does not mean that the Earth actually is at the center of the universe and stationary. The problem here, and probably deliberately, is that they are assuming that there is some absolute frame of reference despite the fact that relativity shows that there is none. They are right that changing coordinate systems does not change reality, but they are using a sleight of hand here. The sleight of hand being used here is that when you are changing between equally valid arbitrary coordinate systems, there is no actual reality to change. For example, under general relativity, neither geocentrism nor heliocentrism represents objective reality, but both are equally valid, being just a choice of a frame of reference. The same thing goes for the Anisotropic Synchrony Convention versus the Einsteinian Synchrony Convention. Neither one represents absolute reality. They are simply equally valid coordinate systems. In conclusion, choosing a clock synchrony convention is an arbitrary choice, and once this is realized, all issues with non-isotopic synchrony conventions go away. Yes, in most cases the isotropic synchrony convention is the simplest, but that does not make it the only valid convention to use. It turns out that this is not only true for clock synchrony conventions, but for things like geocentrism versus heliocentrism as well. As a result, if the Bible is using the anisotropic synchrony convention, there is no distant starlight problem. It is purely an artifact of using the Einsteinian synchrony convention. The fact that it produces a model of galactic redshift that eliminates the need for dark energy is further support for this approach.